Chapter 25 is a paired sample and blocks. We're looking at a matched pairs t-test where we have two matched sets of data and we're looking at the difference between the two. And this is the mean of those differences. We'll look at some examples. Remember when we did our Coke experiment? I think we may have used orange soda. Each of you were paired up with another person with a similar resting heart rate. We called this matching because we had blocks of 2. We took the heart rate before drinking the Coke, and then we took it after, and we subtracted those values to get the difference. Then if we took the average of those differences, we would be looking at a matched pairs. So the mean difference was chapter 24, where you found the mean of 2 independent experiments, 2 independent populations, 2 independent samples, 2 independent treatment groups, and you subtracted those averages. You subtracted the means. Now we're looking at not independent, like a before and after, and we're finding the mean of the differences. And we find this by subtracting the before and the after, or the group 1, group 2, whatever it is, and we find the average of those differences. We're not really doing anything new. The test statistic is the same as the one sample t-test, and the confidence intervals are the same, so we're actually just going to use a t-test with the mean difference and a t-interval with the mean difference. So our t, let me change this color, is x bar d, that's the mean of our differences, minus our hypothesis, which is going to be 0, divided by the square root of s over square root of n. Oops, that's not right. Divided by s over the square root of n. The standard deviation of the differences divided by the square root of n. I was thinking about chapter 24 with the big square root sign. So our hypothesis is going to be that the mean difference is equal to 0. There is no difference. And our alternative is same, big surprise, not equal to, greater than, or less than. The conditions are slightly different. If this is a matched pairs t-test, we need to make sure that we have matched data. And this is how we're going to determine the difference between the matched pairs and the 2 sample t. Are they independent samples or is it matched? The subject has 2 data values that are associated with it usually. We still have to have a randomized experiment or a simple random sample. It still has to be less than 10% of the population. Of course, that applies for samples, but not experiments. And then the nearly normal condition, you're going to check this on the differences. So a graphical display of the differences is what you're going to look at, and you only have one histogram this time, because you're not looking at the before and after data, you're looking at how it changed. So here's our first example. One indicator of physical fitness is resting pulse rate. 10 men volunteered to test an exercise device advertised on television by using it 3 times a week for 20 minutes. Their resting pulse rates, measured in beats per minute, were measured before the test began and then after 6 weeks. Results are shown in the table below, or on the side. Is there evidence that this kind of exercise can reduce? So this is our big question here. Reduce means it's going to be less than 0, the resting pulse rates. So what we're going to do is we're going to find a category, column of the differences here. 73 minus 73 is 0, and 83 minus 79 is 4. So we're going to subtract before minus after, and then a positive number means a decrease. So we have to keep that in mind, that a positive means it's going to decrease and a negative means it increased, which is kind of backwards. We can subtract the other way if we'd like. So Carlos went down 4. David is 1. Edwin 4. Franco 8. Grammy 3. Hans 2. Ivan went up, so that's -1. And George is 3, or Jorge. Okay, so these are our differences. Okay, in our calculator, we're going to want to put the data in list 1 and list 2. Let's write our hypotheses first. That the mean difference equals 0. And our alternative is that the mean difference is greater than 0 because we said greater than means a decrease. And so that reduced it. That's kind of confusing. We maybe should have subtracted the other way, but it's good to see that it doesn't really matter which way you do it. So we're going to look at our conditions. The first condition is the data is matched. The second condition, less than 10%, doesn't really apply because this is an experiment, but 20 or 10 is less than 10% of all men. It's not really randomized because they don't have like a control group. So we're going to only be able to limit what we can say to generalizations are limited to just this group. So our generalizations are limited. We're going to say that because it's not randomized. We don't have a control group. And then we're going to look at our data. So let's get the calculator out here. Let's see. Okay, so I have my data in list 1 and list 2, and then in list 3, instead of subtracting it by hand, I can do second list 1 minus second list 2. You can see it says that there, and then it's going to give me my differences. And it looks like I made a mistake. This should be 76, and then we'll change this to 3. Okay, so now everything I do, I'm going to do it on list 3. So I'm going to look at my second stat plot. And I'm going to look at the list 3, which is my differences. And zoom 9. And it looks straight enough. There's no like major curve in that. So then I'm going to draw that. Sorry for the blurriness. So we're going to say this point over here is that negative. And so normal probability plot is straight enough. Straight enough. So since conditions are met, I will use a matched pairs t-test. With n minus 1, still 9 degrees of freedom. So for the matched pairs t-test, because I'm really only looking at one list, it's just n minus 1. So degrees of freedom, n minus 1. Okay. So now let's look at the actual parts of the test. I need to get my data. So from my calculator, again, I'm going to do my stat calc, one of our stats on list 3, calculate. So I have my x bar D, the mean of the differences is 2.8. My standard deviation is 2.53, and n is 10. So my t is 2.8 minus 0, which is the minus 0 was unnecessary, divided by 2.53 over the square root of 10. So that's 2.8 divided by, and I like to just calculate the Standard deviation, so that later on, if I need to make a confidence interval, I already have that calculated. So that's 0.8. 0.8 divided by 0.8 is 3.5. And then I'm going to do TCDF. Remember, this gives me my p-value from the TCDF. 3.5, 99, 9 degrees of freedom. So 3.5, 9 degrees of freedom gives me 0.00336. So again, our conclusion. Oops. White's not going to work. Let's get black. Since my p-value of 0.00336 is less than my alpha of 0.05, I reject the null hypothesis. There is enough evidence to convince me the exercise program reduces resting heart rate. And okay, so here's our t-table. We're at 95% confident. If you look down here, that's what it says down here. And then we're going to 9 degrees of freedom. That's 2.262. So our t-star with 9 degrees of freedom is 2.262. So our confidence interval is x bar d plus or minus t-star with 9 degrees of freedom times s over the square root of n. Our xd was 2.8 from the last slide, and then t-star was 2.262, and our standard deviation was 0.8. That was the bottom of our t calculation. And then we can do that in the calculator. And we get 0.99 and 4.61. So we can say I am 95% confident the true mean difference in resting heart rate is after the program for this group is between 0.99 and 4.61 beats per minute. We're limited in what we can say about this experiment because we didn't have a control group to compare it to and we didn't have randomization, so we're limited in what we can say. We can say what happened in this group, what the actual true effects would be for this group of people, but we can't really generalize to the greater population without a properly randomized experiment. Okay, so this is some data from last year or possibly the year before, but we gave a quiz and the week before a test, and then we offered a Saturday study session before that test. Here are 20 students' scores who attended the Saturday study session for both the quiz and the test. So here's their quiz score before the study session, and then this is their test score after they attended the study session. Is there evidence that their scores improved? So we put the, or I put the data in my calculator, list 1 and list 2. I don't want to do all that subtraction by hand. So we put that in your calculator, and then here's my calculator. In list 3, I'm going to do L1 minus L2. So second L1, oops, that's not L1, second L1 minus second L2. Okay, that's going to be positive numbers, and a positive would mean an increase in score. So here is our list, and we're going to do everything on this list. So let's do the stat calc one of our stats on list 3, and that way we have this data. Okay, that's off to the side for us. So our null hypothesis is that the mean difference equals 0, and our alternative is that the mean difference is greater than 0, that the scores went up from the quiz. And we'll set an alpha of 0.05. And the conditions, 20 is less than 10% of all students. The sample was possibly representative. Possibly not, because these are the kids that decided to come in on a Saturday. The data is matched. Each student has a score in each category. And then we need to look at the normal probability plot. I'm just going to pull it up real quick. Zoom that again. And I'll take a quick picture of it for you to see. And I'm not sure we can say that that is straight enough. It's pretty curved. Okay. So we would say normal probability plot not straight. Normal probability plot not straight enough. And draw that real quick. I mean, you can see a clear curve there. So proceed with caution. If you get this case on the AP exam, I definitely think you should keep going, but proceed with caution because not all the conditions are met, but if they were, this is what we would do. So proceed with caution for a matched pairs t-test with 19 degrees of freedom. Okay, so here is our data from one of our stats. I'm also going to show you how we would do this in the calculator. So if we do this by hand, t equals 29.855 minus 0 divided by a 15.8 over the square root of 20, which is 29.855 divided by, in your calculator, do 15.8 divided by the square root of 20. That gives me 3.53. And this is 8.45. Now I realize this isn't perfect data because it's not a before and after on the same test. Quizzes are sometimes harder because there's more of the problems concentrated on one topic, but just an idea of how to go through the process. So TCDF 8.45, 99, 19 degrees of freedom. Second distribution, TCDF is number 6, 8.45, 19 degrees of freedom. Gives me a p-value of 3.68 times 10 to the negative 8. Okay, so now let me show you how you would do this in the calculator. If you're doing this in a calculator, you're going to go stat, tests, t-test. You have the data. Your null hypothesis is that mu equals 0. My data is in list 3. My my alternative hypothesis is greater than, and then calculate. And you see we get the same numbers that I got when I did it by hand, 8.45 and 3.6869 times 10 to the negative 8, and that's just rounding differences. so we can say, since my p-value of 3.68 times 10 to the negative 8 is less than my alpha of 0.05, I reject the null hypothesis. There is enough evidence to convince me the test scores improved from quiz scores. Okay, and then if there was no difference between test and quiz scores, there is a 3.68 times 10 to the negative 8 chance, that's pretty small, of obtaining our mean, a mean difference in score as surprising or more surprising than 29.855% increase. And we'll just move some of this stuff up so we can see it all. So then we would want to create a confidence interval for that. To do the confidence interval, I'm going to go stat tests down to t interval. Notice it already has L3 in there. Let's change it to 95 and calculate. And so our interval here is 22 point, we'll write t interval 22.459, comma 37.251, and then we can say I am 95% confident the test scores are between 22.46 and 37.25% higher than the quiz scores. Okay, so the next one is the Boston Marathon had a wheelchair division since 1977. Who do you think is typically faster, the men's marathon winner or the women's wheelchair marathon winner? Because conditions differ year to year and speeds have improved over the years, it seems best to treat these as paired measurements. Here are the summary statistics for pairwise differences in finishing time in minutes. The female wheelchair winner minus the male running winner. There's 28 different years, and the mean was 0.089286 with a standard deviation of 37.7. So our null hypothesis is that mu d equals 0. In the alternative, it says differences, let's see, who do you think is typically faster? So we want to know what's the difference not equal to. Mu d does not equal 0. And let's set an alpha, 0.05, conditions. we have data is matched. We have 28 is less than 10% of all marathons. The data is representative. And we're going to assume nearly normal. .28 isn't greater than 30, but it's close enough to use the central limit theorem. So since conditions are met, a T model is appropriate. I will use a matched pairs t-test with 27 degrees of freedom. And so we have the mean and standard deviation. So our t is 0.089286 over 37.7241 over the square root of 28. Do that in the calculator. 0.089286 divided by 37.7241. That divided by the square root of 28 is 0.0125, and then TCDF for our p-value 0.0125, comma 99. Because it's positive, we're going to do comma 99. If this was negative, we would do negative 99 on a not equal to test, and 27 degrees of freedom. So stat second vars, TCDF, my answer, comma 99, 27 degrees of freedom. Plug it all in. We get 0.495, and we have to multiply that by 2, and we get 0.99. Now, if we were doing this in the calculator, let's show you how to do that with the calculator. So I literally just did all of this, but I didn't have it recording. So stat test t-test. I'm going to select statistics, stats there. Instead of data, my mu naught is 0. Put in my mean and standard deviation, my sample size. Select not equal to. It's so important we select that one correctly, and then hit calculate. And notice I got the same thing that I got when I did it by hand. Okay, and so we write our conclusion. Getting redundant yet? We should be really good at writing these conclusions. Since my p-value of 0.99 is greater than my alpha of 0.05, I fail to reject the null hypothesis. There is not enough evidence to convince me the men's winning time is different from the women's wheelchair winning time. Isn't that interesting? Let's see, let's add a little punctuation in here. Or not. No. It doesn't want to let me do that. So now that we've done 5 different tests, the question is, how do you decide which test to use? We have 5 tests in our arsenal: the 1 proportion z-test and interval, the 2 proportion z-test and interval, the 1 sample t-test and interval, the 2 sample t-test and interval, and the matched pairs t-test. So the first thing you look at is, what type of data are you given? Are you given mean and standard deviation, or are you given a proportion? Whether that's like successes over total number or actually a percentage. If it's a proportion, we're going to use a z-test. If you have one proportion with one sample size, you're going to do a one proportion z-test or interval. If it's a two proportions with two different sample sizes, you're looking at the two prop z-test or interval. And it should ask you in the problem to either do a significance test or a hypothesis test or create an interval. And then if it's a mean, it's got to be a t-test. If you have a single mean with a single sample size, you're looking at a t-test or interval. If you have two independent means and you have two sample sizes, you're looking at a two sample t-test. And if the data is matched, it's before and after, then we're using the matched pairs. What are the conditions? The conditions that are the same for all of the tests are simple random sample, less than 10% of the population, and is there independence? For the matched pairs, you're not looking for independence, but showing that it's definitely not independent. And then these two depends. If it's a mean, you're looking at nearly normal. And if it's proportions, you're looking at success failure. There is absolutely no way of calculating success failure if you have a mean, because you do not have an NP, or you don't have a P to do NP and NQ. And then you go through the same steps for all of them. Write your hypotheses, check your conditions. Sometimes it helps to draw the model, state which test you're using since conditions are met, blah, blah, blah. I will use this test. Perform your test by finding your Z or T score, calculating your p-value, and then you interpret your results.